Most of us grew up with a simple story about the end of the dinosaurs. A giant rock falls from space, a massive fireball sweeps across the planet, and the T-Rex is gone forever. But if you follow modern scientific research, the story is more complicated. Conflicting headlines point to asteroids, megavolcanoes, or long-term climate change, making it difficult to determine which event actually triggered the collapse. To find the answer, geologists look at this. This is the KPG boundary. It's a distinct geological line found in rock layers all over the world, marking a singular event 66 million years ago, where 75% of all plant and animal species vanished from the record. The fossil record shows a very specific pattern of loss. The event was powerful enough to eradicate multi-ton predators, but managed to spare delicate frogs, small mammals, and certain lineages of birds. A giant fireball is a simple story, but it doesn't explain that selectivity. Finding the true culprit means finding a mechanism that accounts for both the mass death and the specific survivors found on either side of this line. Trying to pin down that mechanism has triggered a famously fierce academic debate, one that paleontologists literally refer to as the dinosaur wars. The arguments center on precise timing. Rival teams use isotopic dating, measuring the radioactive decay of elements in ancient rocks, to argue whether the extinction was a sudden shock or a slow, grinding decline. These theories fall into three categories: fringe theories, volcanism, and the Chicxulub asteroid. Evaluating them requires three criteria: high-quality geological evidence, a global kill mechanism, and a logical reason why certain species survived while others didn't. By examining the trade-offs within each model, we can see how well they align with the physical evidence found at the KPG boundary. We will start with the fringe theories. Over the decades, researchers have suggested everything from mammals eating dinosaur eggs to the rise of poisonous plants, or the slow effects of continental drift. These ideas aren't entirely baseless. They can explain why a specific, localized population of dinosaurs might have faced a gradual decline in the millions of years leading up to the end, but they fail a major geological test. None of these localized problems explain the sudden wipeout of complex marine life, like these coiled ammonites, happening simultaneously across the planet. Our second suspect is the Deccan Traps. In what is now western India, massive, continuous volcanic eruptions pumped out lava spanning over 1 million square kilometers. This level of volcanism releases an enormous volume of greenhouse gases. Research indicates this led to ocean temperatures rising 7 to 9 degrees Celsius, paired with severe acid rain. This mechanism explains the fossil record just below our extinction line. The rising heat and acidifying oceans show a biosphere under immense, long-term stress well before the mass die-off. However, the volcanic theory has a missing link. It struggles to account for the abrupt global rock layer at the KPG boundary, which is packed with iridium, a rare metal heavily concentrated in asteroids, not magma. While the Deccan Traps poisoned the atmosphere and weakened the global food chain, volcanism alone lacks the immediate trigger required to draw that sharp physical line in the stone. This leads to the Alvarez hypothesis. In 1980, scientists proposed an asteroid impact, and a decade later, geologists located a 120-mile-wide crater hidden right here under the Yucatan Peninsula. The evidence is consistent globally. That dark band of sediment we saw earlier contains iridium concentrations hundreds of times higher than normal, directly linking the rock record to a spaceborne impactor. When it hit, it vaporized the seabed. Billions of tons of dust and sulfate-rich rock were ejected into the upper atmosphere, blocking the sun and collapsing the photosynthesis that supports the food chain. The scale of the object explains the energy release. This is a space rock 10 to 15 kilometers across, significantly larger than Mount Everest, hitting the Earth with over 1 billion times the energy of the atomic bombs used in World War II. But even this model has a biological trade-off. Standard impact models predict a deep, instant freeze. If the Earth plunged into a brutal, immediate winter, it's difficult to explain how temperature-sensitive animals, like frogs and salamanders, made it through. The iridium and the crater prove a massive catastrophe occurred. However, relying solely on the brute force of the impact leaves questions about the specific survivors found in the fossil record. In recent years, researchers at UC Berkeley developed a unified theory that bridges this gap. It's known as the 1-2 punch. Their model proposes that the Chicxulub impact generated seismic shockwaves so immense they rippled through the Earth and accelerated the ongoing Deccan volcanic eruptions on the other side of the planet. This creates a dual disaster scenario. An immediate impact winter collapses the food chain, followed by 100,000 years of extreme volcanic climate volatility that prevents a quick recovery. This combination matches the physical evidence. It provides the sudden asteroid strike needed to create the sharp iridium boundary and the sustained volcanic activity that explains the delayed biological recovery. The scientific consensus suggests we aren't looking at a single cause, but a highly complex interaction between two global events. This flowchart illustrates the biological filter created by a collapsing global food chain. The question shifts to how it filtered life by trait. During a prolonged impact winter, plant life dies. Massive herbivores require massive vegetation daily. Without it, they starve, and their predators follow. For millions of years, physical size was an advantage, but when the food chain collapsed, the caloric cost of a massive body became a liability. Compare that to the surviving avian dinosaurs. They were small, and many were equipped with a beak and a muscular gizzard. When forests died, these birds could locate and digest hard, dormant seeds buried in the soil. They were able to extract energy from a landscape that offered no fresh food. Survival favored a small body mass, the ability to burrow or dive, and a flexible, generalist diet. While the impact and the volcanoes cleared the landscape, the survivors were determined by their own biological constraints. The KPG boundary shows that when global food chains fail, small-scale efficiency becomes more valuable than sheer physical power.